Okay, so this is the next video for section 6.4, and we'll continue to talk about logarithmic functions. In this video, we're going to focus on graphing. Okay, as I mentioned on the first video, the logarithmic function is the inverse to the exponential. So, if we are looking at the first example on your study guide, just continuing from the last one, we're asked to sketch two graphs, and that is y, or f of x, is equal to 2 to the x, and g of x is equal to log base 2 of x. So these two functions are inverses of one another, which means their graphs will be symmetric with respect to the line y equals x. And it also means that we can use one graph to help us look at the other. We already know how to graph y equals 2 to the x. Remember, it has a horizontal asymptote, y equals 0, or the x-axis. We know the point 0, 1 is on the graph, and we also know the point 1, 2 is on the graph. So 0, 1 would be about here, and 1, 2 would be about here. So we know the graph of y equals 2 to the x looks something like this. Okay, so now let's take a look at what we can come up with for y equals log base 2 of x. So if 0, 1 is on the graph of 2 to the x, then I know that 1, 0 will be on the graph of its inverse. So 1, 0 is on the graph of this function, and since 1, 2 is on the graph of 2 to the x, I know that 2, 1 will be on the graph of its inverse. And likewise, since we had a horizontal asymptote of y equals 0, in this case I will have a vertical asymptote at x equals 0, or the y-axis. So this function will look like this. So this is my log base 2 of x, and this one is 2 to the x. Again, symmetry with the line y equals x. Okay, so let's talk a little bit about this. Properties of graphs of logarithmic functions, and this is the list at the bottom of the study guide. So for f of x equals log base a of x, where a is greater than 1, just like we broke the cases up with the exponential functions in class, this will pertain to when the base is greater than 1, and then we'll look at the case when the base is in between 0 and 1. So again, the function is increasing. It rises from left to right. The graph includes the point 1, 0, and if we're talking general form, we will just fill this in for the general log base a of x. So it would include point 1, 0 and a1. We use 2, 1 here because we were talking base 2. So now let's look at the graph. As x approaches infinity, so as I travel to the right on the x-axis, the value of the function, or y, or f of x, will continue to go up forever. So f of x approaches infinity. As x approaches 0, so as I go this way towards 0 on the x-axis, my graph approaches negative infinity. So the domain of this function is only the positive reals. Remember, x equals 0, or y equals 0, excuse me, the x-axis is a vertical asymptote that this graph will never touch or cross. So the domain is 0 to infinity, and the range is negative infinity to infinity. Okay, now let's look at our second case when a is in between 0 and 1. So we will graph y, or I think your sheet says f of x is equal to 1/2 x to the x, and g of x is equal to log base 1/2 x on the same set of axes. And since they're inverse functions, again, their graphs should be symmetric with the line y equals x. So let's go ahead and graph y equals 1/2 to the x first. So remember, we know that the point 0, when x is 0, f of x is 1. And when x is 1, f of x is 1/2. So I can plot those 2 points, 0, 1, and 1, 1/2. Again, I know that I have a horizontal asymptote, and that is the x-axis, or y equals 0. And so this is a decreasing function that looks like this. Okay, so now let's go ahead and graph log base 1/2 of x. So again, using the fact that they're symmetric with respect to the line y equals x, I know the point 1, 0 is on this graph. So that would be right here. And 1/2, 1 is on this graph. And then I also know that I'll have a vertical asymptote, and that will be the y-axis, or x equals 0. And so this graph will look like, oops, I'm drawing a little cockeyed. That'll be a little bit straighter. Okay, so the red, again, is log base 1/2 of x, and then this one is our exponential, and that is 1/2 to the x. So to go through and go ahead and identify these properties at the bottom there of the study guide, again, let's just do that in general for y equals log base a of x. So we can say that this function, again, when a is in between 0 and 1, is a decreasing function because it falls from left to right. The graph includes the points 1, 0, and a1. Now, as x approaches infinity, f of x also approaches infinity. So as I go to the right on the x-axis, the function will actually go to positive infinity. And as I look to the left, so as x approaches 0, the graph will continue to go up forever. So as x approaches 0, f of x approaches infinity. So the domain, again, is just the positive reals, not including 0. And the range is all real numbers. Okay, and let's continue on. So now if I'm going to Okay, let's go ahead and continue on to the next page, and we're going to just talk briefly about reflecting and shifting the graphs of log functions. So this example says graph y equals natural log of x, and then also graph, let's see, we'll pick different colors for these, y equals negative natural log of x, and lastly, graph y equals the natural log of negative x. So let's do that on the same set of axes, and we'll talk about the different ways that these will be reflected. So let's start with natural log of x, so the first one. So remember, natural log of x is base e. So this means that 2 points on my graph will be 1, 0, and E1. So 1, 0 will be about here. And remember, E is about 2.7. So E1 will go out to almost 3. That would be about here. The y-axis is a vertical asymptote. So our graph looks something like this. Alright, so that's y equals natural log of x. So now if I'm going to graph negative natural log of x, remember this is an example of y equals negative f of x, which indicates an x-axis reflection. So if I'm going to reflect this about the x-axis, that means that the point 1, 0 will still be on the graph, because that means, remember, for every point xy on the graph, if I'm reflecting about the x-axis, x negative y will also be on the graph. So 1, 0 doesn't change, but instead of E1, I would have E negative 1. So an excuse me, an x-axis reflection will look something like this. So that's y equals negative natural log of x. And finally, natural log of negative x would indicate a y-axis reflection. Remember, because we're looking at y equals f of negative x. So a y-axis reflection instead of xy, when we reflect it, remember we're talking about a point here and then over here. So that would be negative xy would also be on the graph. So again, we're basing this off of the original function, so the red one. So instead of 1, 0, I would plot negative 1, 0, and instead of E1, I would plot negative E1. So my y-axis reflection, I'm getting a little jagged, would look something like that. And take a quick look at the domain and range for each. So let's start with y equals the natural log of x. So the red function, the domain is the positive reals, so from 0 to infinity. And the range, it goes up and down forever, so that's negative infinity to negative infinity. The same would be true of negative natural log of x. Again, the range is all reals because this will go up and down forever, and the domain is just the positive real numbers. But now for natural log of negative x, again, the range is the same. This thing goes up and down forever, but we just want the negative real number. So this would be from negative infinity to 0, not including 0. Okay, I'm going to stop this video here, and although I believe I told you there were 2, I'm going to do a third to just show you a couple more examples. I want to algebraically find the domain for you, and then also talk about how to algebraically find the inverse, specific with exponential and logarithmic functions. So we'll stop this one here, and 2 more examples on video 3.